Hi, so in this video we're going to be talking about fatty acids. Now what are fatty acids? As you can understand from the name, they have two components. The first one is given by the fatty part, which is this part to the right, all this chain here. Now fatty acids are composed by a fat part, which is hydrophobic, which is made by this carbon chain. Now each carbon is bond to 2 or 3 hydrogens. So here we're gonna have like hydrogen, here another hydrogen, and this like all over the chain. And the last carbon is bond to 3 hydrogens because, okay, that's a hydrogen, because he's not bound to another carbon. All these bonds are single bonds. This example, and here there's going to be other hydrogens here, 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 and so on. Now, all these hydrogens are bonded with a single bond, and carbon to carbon are bonded with single bonds because this is a saturated fatty acid. So what does that mean, saturated? It's that all the carbons are bonded with single bonds. So the chain is going to be made by CH2, CH2, CH2 repeated up until the last CH3. So we're going to have something like this, CH2, yeah, that's a 2, in parentheses, repeated n times as many carbons as there are over here. And then it's going to end with CH3, so remember that. You must count the carbons, excluding the last one, and excluding the first one in this type of writing over here. Then there's going to be a right over here, a COOH. Now that part regards the, so this is for saturated fatty acids. Saturated saturated fatty acids, which can be written like FA, fatty acids. Anyways, now let's go back to the acid part. What is that represented from? It's represented by this part over here, which is a carboxylic group. Now, as you can see, there is a carbon which is bonded to an oxygen atom with a double bond, and with an OH with a single bond. Now what happens is that at a pH, which is our pH, which is about 7.2, 7.4, this is the pH value in our bodies, more or less. Well, you cannot change that much, so it's got to be between these values. This is pH. What happens is that this group loses this proton right over here. So it's going to be C with a double bond to an oxygen, and then a single bond to an oxygen which is negatively charged. And then there's the fatty part, which you're going to write like an R, which means a lateral chain. This plus a H plus. This is the proton or hydrogen ion, which has detached by this oxygen. Of course, this proton, it's never going to keep his electron becoming a hydrogen atom, because the electronegativity of oxygen is much bigger than the one of hydrogen, so oxygen, wins to keep the electron. And there is also one other fact. This oxygen right over here has a partial negative charge because the difference of electronegativity is greater than 1 yet smaller than 2. So it's not a ionic bond, but it's a polarized bond. In fact, bonds can be nonpolar if the difference of electronegativity, I'm going to write it like this, remember it's the difference of electronegativity. So the electronegativity of 1 minus, this is the electronegativity of, say, oxygen, minus the one of carbon, gives you a certain value, which can be in between 0 and 1. In that case, you have a non-polar bond. So, and that's, by the way, the bond which is exists between the carbon and the hydrogen. In fact, being this bond nonpolar, in fact, the difference of electronegativity of carbon and hydrogen is about 0.4. So there's not going to be any partial charges between these atoms in the fatty part chain. And that is why, by the way, they will not interact with water. But we're going to talk about that later. If the difference is in between 1 and 2, well, then you're going to have a polar bond. And if it's greater than 2, we're going to have a ionic bond. If it's greater than 2, we're going to have a ionic bond. For example, NaCl, it's Na plus Cl minus. By the way, if you see these two elements on the periodic table, this is very much the chloride part. It's very much to the right, and the sodium, it's at the extreme left. So that tells you at the very left they have a small electronegativity. At the right they have a big electronegativity. This is you must remember to exclude the elements which have which are the noble gases and stuff like that, which have their electronic configuration all filled with electrons. So anyways, going back to our fatty acid, all the chain over here has non-polar bonds. So what happens is that this is going to be hydrophobic because water normally interacts. Water is done like this: hydrogen, oxygen in the center, and hydrogen here. Now what happens is that oxygen has a partial, this symbol, by the way, is a delta. It's a Greek letter which represents a partial charge in this case. And here there's going to be a partial plus, and here there's going to be another partial plus. So the electrons are going to tend to go more next to the oxygen rather than next to the hydrogens. So what happens is, normally if you put NaCl in water, the water molecules are gonna go all around the sodium, being close to the sodium, which is Na plus, being all close with the oxygens around here. Then you have two hydrogens, and this is going to happen all around the ion. That's another oxygen, then oxygen, and that happens all around the ion. So all these oxygens are partially negatively charged, and they're going to interact with the positive charge of sodium. Same thing will happen with chloride, which interacts with the hydrogens in the water molecule. Here, there are, in the fatty part of the chain, there are no polar charges. There's no polar bonds, so there aren't any partial charges around the chain. So it's not gonna interact with water, and that's what gives it its hydrophobic characteristics. So water would prefer to interact between itself rather than interacting with this chain with which they cannot interact. The only part they can interact with is this part over here, the acid part. That's why these molecules usually are present in water as small spheres in which the external part contains their polar heads. This is the polar group, the polar head. This is the hydrophobic chain, which here are all around are the polar heads, and in the center there are the hydrophobic parts. And I'm going to explain why I'm doing these zigzag chains. Okay, so I did these because, as you can see right over here, the chain is represented as a line with many angles, and those angles can actually be represented just the way I'm drawing it right now, with the final C, O, O minus, or OH as you want. I mean, depending on the pH. And each vertex is gonna be CH2. So here's CH2, CH2, CH2. At the end, CH3 right over here. That's a quick way of representing saturated fatty acids.